Mindsetters, welcome to today's Grade 12 Physical Sciences show. Today we have a special revision lesson on organic chemistry. We have selected highlights of lessons shown early in the term to help you revise Term 1's work. Please post all your questions and comments on our Facebook page on facebook.com/LearnExtra or on Twitter @LearnExtra so we can help you with your revision. Don't forget to download today's show notes on learn.mindset.co.za or click on the link on our Facebook page. Now it's time to get on with our lesson.
Now, what we're going to do with question 1 today is we're going to draw structural formulae. If you can draw the structure, then naming becomes a lot easier. Okay, so you're going to get a couple of these. This isn't really what you're going to see in an exam, but this is where we're going to start. And then question 2 that we're going to do now will be a more of an exam type question. Okay, so they ask you to draw the structure of heptane. Okay, it's heptane. So the first thing we go is we recognize and we say, fine, hept means 7. So that means it's 7 carbons, but it's ane, 7 carbons with only single bonds between them. Okay, so that means I've got to draw 7, so I'm going to go 1, 2, 3, 4, 5, 6, 7. Okay, but that is not the structure. Please be careful here. Sometimes we try and get a bit lazy, and we go, well, each of these carbon atoms have to have 4 bonds, so we know all of these are going to have a little hydrogen. And then sometimes we get lazy again and we say, there we go, that's my structure, and you won't get any marks for this because you have to draw in every single hydrogen. Every single one. Okay, don't get lazy. Also, please, grade 12s, you got to consider that your markers, some of us are getting old now, so we need help when it comes to reading your handwriting. And sometimes when you draw these so tiny that actually we can't tell the difference between the bond and the hydrogen. And when you're tired because you've been marking for 11 hours a day for 4 days, things get missed, and you don't want that, okay? Or you're struggling to see. You want to make it as easy as possible, so don't make it as small as possible. Obviously, don't make it the whole page, but make it big enough to read nicely, okay? Then, 2-butene, which can also be written, and this is more the way you're probably going to get it in your exams, is it's written as but-2-ene. Okay, now this is quite important because butene has got 4 carbons, 4 carbons in the longest chain, okay? So we're going to write 4. 1, 2, 3, 4. Now they're saying to me that it's but-2-ene. The ene means there's a double bond. That double bond can sit in a couple of places between the first and the second carbon or the second and the third carbon. So we're going to go, okay, well, I need to know where it sits, which is what the 2 is for. So the 2 tells me that my double bond sits on my second and third carbon. So the 2 is the number of the first carbon it sits on. So it's between carbon 2 and carbon 3. Now we need to fill up with hydrogens. First one's easy because this will become 1, 2, 3. Now we get all excited because we know we need to fill up with hydrogens, but we forget, as special as carbon is, it can only make 4 bonds. So we look at this and we go, well, that carbon already has 1, 2, 3 bonds. That means I can only add 1 more hydrogen. Remember last year you did Vesper, you did molecules, you did shapes, you realized that atoms like to be as far away as possible. So we really should draw the hydrogen on that carbon at the bottom, okay, because they want to be as far away from each other as possible. It's like you trying to share a room with your sibling, okay? We all know how well that goes sometimes. And hydrogens at the end. So that one was fairly straightforward. Okay, then 2-methylpropene. Wow, now it's starting to get a little, okay. Well, there's several things here. We've got 2-methyl, so the methyl sits together. Then we have prop, and then we have ene, okay. The methyl is a branch. It's attachment. It's like the garden cottage in the house. Okay, it's an attachment to this. The propene is my longest chain. Prop means 3. So that means I'm going to have 3 carbons. 1, 2, 3. Now I've got an ene. Ene means a double bond. And I'm pretty sure some of you are going, but Tracy, that didn't tell me where that double bond can be. That's because there is only one place it can be, which is here. Okay? Or not, which is there. Now, before you start screaming at the TV and go, but wait, Tracy, it can also be between the other two. Okay? So in other words, you're saying to me that I can do this. Actually, that's just a mirror image of that. They mirror images. We've just turned it around. It's the same thing, which is why I don't put the numbers in, okay? So be careful there. So let's take that away. But we're not done, because now we need to do the methyl group. And it's on the second carbon. 1, 2. Okay, let's do it over here. Methyl means meth is 1 carbon. Methyl, or your alkyl groups, which are branches which we put on top, they look like alkanes, but instead of being a long chain, they're just an alkane missing a hydrogen, which we attached to the chain, okay? So methyl means we've got 1, there's the 1, has 3 hydrogens, okay? This carbon's going to have 3 hydrogens. And now we've got to go, let's see about the one in the middle. 1 carbon, 1 bond, 2 bond, 3 bond. It's already got 4 bonds. I can't have any more. And 1 hydrogen, and 1 hydrogen. Now I draw the hydrogens out to the side, grade 12s, because we want them to try have as much space away from each other as possible, okay? Then we've got methanol, A-L, not O-A-O-L. So it's not an alcohol, it's an aldehyde, okay? The most famous aldehyde is formaldehyde, which if you do life sciences, you know when they keep all those like specimens and stuff in jars, it's full of formaldehyde. And in fact, our life sciences have got like a baby pig, I think it is. Sorry, oops, I didn't do that. It's about this. I can't actually go into the biology labs because of it. But, I just can't.
Shame on you.
No, it's a baby pig, man. That's cute. It shouldn't be in a jar. That's why I think I'm just going to stick to my subject. How does that sound?
Please.
Okay. Meth. Meth means 1. Aldehyde means double bond to an oxygen. So there's 1 hydrogen over there, and there'll be 1 hydrogen over there. That's methanol. Nice and easy. Ooh, look here. Methyl ethanoate. Oh boy. This is an ester. Esters are wonderful things because their names are really easy and the way they're drawn. The methyl, just as quickly, comes from the alcohol that made it, which means this comes from methanol. Okay. And the ethanoate part comes from the acid that we used. It's an alcohol and an acid put together. And this comes from just pretend that's an H, ethanoic acid. Okay? So, methyl, the first part of this, methyl means 1, so we're going to have a single carbon. Then we have a second part that says ethanoate. That means we have another part that has 2 carbons. Okay, what joins the 2 together? An oxygen in the middle. Right here is an oxygen, okay? But now we've got there's one more thing. An ester has a double bond to an oxygen as well. And that double bond oxygen always goes to the part that's from the acid. So it comes over here. And now the rest is just hydrogens. So we have a hydrogen over here. This is a nice colorful molecule. It's beautiful. Okay. And each of these has 4. The carbon, my first carbon with all the oxygens on, cannot have any hydrogens, otherwise it has too many friends. Okay, carbon likes friends, but carbon only likes to have 4 friends at a time. Can't have more than 4 friends at a time. It gets it just can't handle it, okay? So it's 4 friends at a time. Then the last one that we're going to do on this question is propanol with an O. Okay, 1, 2, 3, but there's a problem with this name. I haven't told you where to put the OH, because it can go on the first one or the second one. So let's put it on the last one. I really should have named this propan 1-ol. O, H. Guys, whether you draw that OH coming up, going down, or to the side makes no difference. Okay, it's the same thing, it's just in a different position. So those are all hydrogens. Okay, so we make it nice and neat, which is not what I have right now, but I'm blaming the board. Okay, naming nice and easy. Okay. Okay, this is adapted from question 3 from the November 2010 paper, this one. So this is what you're going to get. The chemical properties of organic compounds are determined by their functional groups. The letters A to F in the table below represent 6 organic compounds. Now, grade 12s, before you even look at the question, I'm not even going to scroll up, look at what they've given you and see if you can name them, see if you can identify what they are. So we look at these and we go, over here, I have a double bond to a carbon, which means this is an alkene. Okay, let's figure out what we know what they are. Okay, this one only has single bonds, but then I have a halogen over here, which means this is a haloalkane. Okay, over here, C only has single bonds with all of them, which means it's an alkane. Okay, I'm not even worrying about naming them right now. Methanol means it's an aldehyde. We actually just drew it. Okay, so that's an aldehyde. This has a double bond oxygen with an OH at the end, which means it's one of the acids. I'm going to run out of space to put carboxylic acid there. And then they name methyl methanoate. It's the only one where we have a double barrel like that, so it's an ester. Okay, now, the reason why I've done that is because in the question over here, it spoke about functional groups. So they're probably going to ask me something about the functional groups along the way. Okay, so I've identified all the functional groups. Okay, we could also go further and now name each of these compounds. I'm not even looking at the question. And as much as you're saying, oh, but Tracy, we're wasting our time, what if they don't ask? That's not the point here, grade 12s. I'm trying to teach you some stuff about how to answering, and you're going to see by the time we actually look at the questions, it's going to be so easy. You're going to breeze through the questions because you've spent time interacting with the question. Okay, so let's name these. We have 4 carbons in the longest chain. 4 carbons in the longest chain, it's an alkene, so that makes it butene, but I need to number where the double bond is, and it's on the first carbon. Okay, it's between 1 and 2. I'm going to go, I don't always number from left to right. I'm going to make it get to the smallest address possible. So from left to right, in this case, it's on the first one. So this carbon's name, this compound is but1ene. Okay? My next one, it's a little more difficult, and I'm going to put it at the top. So we go, let's see, 1, 2, 3 carbons if I go that way, 1, 2, 3 carbons if I go that way, 1, 2, 3 carbons if I go that way, but I can't use that as my longest chain because it's got to include the bromine. Okay, it's got to include the bromine. So I'm going to make this part my longest chain. That's 3 carbons in the longest chain. That makes it propane. Okay, don't have to number anything for the propane part. Attached to the propane is a bromine and a methyl group. We just drew a methyl group, okay? And we go, well, where are they? Well, the bromine is more important than the methyl. So the bromine must go on the smallest. It's got to be first in the street. So that's 1 bromo, because that's where it lives, 1 bromo. And the methyl sits on 2. So it's 1 bromo, methyl, and you can't read that, propane. So let's just pretend you can read it. Now this last one that we're going to do here, 1, 2, 3, 4, 5, 6 in the longest chain. That means meth, eth, prop, but, hept, pent, hex. Hex is 6. So I know this is going to be hexane. I'm going to write it over here because I've run out of space. Okay. And now we've got a methyl group on that carbon and a methyl group on that carbon. There's 2 methyl groups, which makes it dimethyl. Okay, all of this becomes one word. So it's dimethylhexane, but I need to say where the methyl groups live. So watch what happens. Now, if I number from left to right, I go 1, 2, 3, 4, 5, 6. Then my numbers for my methyl group goes on the 3rd carbon and the 5th carbon. And we go, okay, that's an option. But let's see what happens if I go the other way around. So now I go 1, 2, 3, 4, 5, 6. So instead of using 3 and 5, I can use the numbers 2 and 4. So this becomes 2,4-dimethylhexane. Okay, you must have it on the smallest numbers. They don't like big numbers. They really don't. And this last one here, I'm not going to worry about drawing the others because I don't have enough space there. That's ethanoic acid. 2 carbons in the longest chain. So this is ethanoic acid. Now, I know we've just spent 5 minutes spending some time looking at what functional groups we have, what series they belong to, what their name is, but that's okay, because now watch what happens when we answer the question. First question, write down the letter that represents the following, an alkene. Oh wait, hello, we did that already. It is A. Done. Don't even have to think about it. Which one represents the aldehyde? D. We did it right at the beginning. Look at that. Took me 30 seconds. Not even. Okay? Then, the next question, write down the we've done it already. The IUPAC name of compound B. We already did it. 1 bromo, 2 methyl propane. So let's actually write it down nicely so that somebody can actually read it. So it's 1 bromo, 2 methyl. Look at that. You can actually read my handwriting. Propane. Done. I don't even have to think about it. So even though I've just spent 5 minutes interacting with it, when it comes to writing the question, it's easy as pie because we've done it already. And then, which we just did this last one, number C, 2,4-dimethylhexane. So we're going to write that in here as well. 2, 4, that was terrible. That's even worse. 2, 4, dimethylhexane. Nice and easy. Ooh, write down, we knew this was coming, the structural formula of compound D. Compound D is methanol. We've already done that once today. Methanol, double bond oxygen, done. Write down the name of the carboxylic acid shown in the table. Where was the acid? It was E. We've already done that. We just need to write it in. Don't even have to think about it. So that was ethanoic acid. And then the last question here is write down the structure for the formula of F, which is methyl methanoate. We like that one because it's actually the easiest out of all the esters. Methyl, 1 carbon, methanoate, 1 carbon, double bond oxygen, hydrogen, 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 hydrogen. Really not so bad. Okay, so I'm hoping that helped.
Alright, Mindsetters, I hope you guys are enjoying this revision session. Remember, if you are struggling and need help, please post your question on our Facebook page or send an email to helpdesk@learnextra.co.za. Now it's time to take a quick break, so don't go anywhere. We'll be right back. Welcome back, guys. I'm sure you've seen and heard about the Mindset Rack nomination and hope you'll get involved. If you make a video, post it on YouTube with the title #LearnExtraRack followed by your name or the name of your group. If you don't have a video, post a photo on our Facebook page and tell us what you've done. Let's use this short holiday to make a big difference in other people's lives. Now, let's get back to revision.
So here's a previous exam paper question on this very topic. And I want to go through them very slowly and make sure you understand the factors that influence intermolecular forces. What are the physical factors that can be affected? You need to make sure that you revise all of those physical factors and you understand to be able to explain changes in boiling point, melting point, vapor pressure. Very, very important. What affects them? And we just started the little recap. We didn't get very far. But I want to get into the questions now. So, here we go. Hydrocarbons are simple organic molecules or compounds. The homologous series called the alkanes. Now, guys, is one of the groups of hydrocarbons. Alkane, you should be remembering, CN, H2N plus 2. It is saturated. That means that they have carbon-to-carbon single bonds. And all 4 bonds are taken. There's no double bond. It's just carbon and hydrogen. And that's an example of one that I've just drawn there, which has 3 carbons in it. And it has how many hydrogens? Well, CN, 3, H2N plus 2. That means it's 3 times 2, which is 6, plus 2, which is 8. Let's check if that's right. It does work. There are 3 hydrogens. There are another 3 hydrogens, the methyl groups on the end, and there are 2 hydrogens. So it gives us C3H8. Name of it, 3 carbons, means propane. Okay, we've just done a little bit of revision. Now it says, one physical property of the alkanes is shown in the table below. And so the property we're looking at is boiling point. And we're looking at the boiling point of the isomer as well. And here we go. We're starting with methane. Meth is 1 carbon. Eth means 2. Bute means 4. Pent means 5. And hex means 6. You need to know that. What's the trend? Notice this starts at minus 161 and it ends up at 68. And so there's an increase in the boiling point, which is quite interesting to have a look at. Now, let's have a look at the question. Define the concept of homologous series. Now, it's apart from the fact that it's a tongue twister to actually say homologous series, we need to know the definition. The definition, it's like a family, but the accurate definition is it's a group of molecules with the same functional group. And a general formula. So all the members of this family or this group obey the general formula. You can write down the general formula. We did it earlier, and we said for the alkanes, CnH2n plus 2. So there's the general formula. What do we mean by this word functional group? Okay, this is the characteristic of what makes the molecules belong to that family. Okay, so they all fit in with the same naming structure. So if you think about a traditional family, everyone has the same surname. In this homologous series, everyone has the same general formula. But they also have a shared characteristic that makes them behave in a particular way. They all behave in a certain way because they've got this particular characteristic. And the characteristic that we're dealing with the alkanes is that they all have single carbon bonds. Now, that's just the functional group. That's what determines how they react to each other. It determines whether it's polar or non-polar. It describes their physical properties. So we need to recognize the idea of homologous series. We can add to them. There are lots of homologous series. There's the alkanes, the alkenes, the alkynes. You also need to know about the alcohols. You also need to know about the aldehydes, the ketones, the esters, the carboxylic acids. Very, very important that you know the different functional groups and the homologous series to which they belong. Very good. Let's move on. Question 1.2. Explain the change in boiling points of the alkanes from methane to hexane. So let's have a look. We've been given it. Methane at minus 161 degrees Celsius. Hexane 68,7 degrees Celsius. That means that this is a liquid at room temperature. This is a liquid at room temperature. Whereas these are all gases at room temperature. At 25 degrees, they will not have, these ones will not have boiled. These ones will boil this one, 35 degrees, 34 degrees, it will still be a gas at room temperature. Room temperature is 25 degrees. So all of these, they will not boil above 25 degrees. So these are gases. This one is, pentane is still a gas at 25 degrees. Only hexane is a liquid at 25 degrees. Hope you've got that. The important thing is that the temperature, the boiling point, is increasing. So let's write down how we would do it. First of all, let's write down what it is. The boiling point increases with increasing mass, or we can say chain length. Because they're all alkanes, we know that they're all long single chains. That's the traditional way of joining them. And we recognize as they get longer and longer, they've got a bigger surface area. And so that's the important thing. They're all of the same nature. They're all non-polar molecules. They're non-polar molecules. But it's important to recognize longer chain, there's a longer chain, like in hexane, which has got 6 in the chain, there's a bigger surface area. And if there's a bigger surface area, guys, have a look at this. It's really important for us to see. If I draw a little molecule and another little molecule here, the forms of attachment, the places of attachment are relatively few. But if I draw a big molecule, long chain, can you see that there are more places that these molecules can have intermolecular forces? Now remember, I said these are non-polar molecules, so they are only temporary. They are relatively weak. They're an example of London forces. They're temporary dipoles. And that's why the boiling points, it doesn't take much energy to break them apart when they're little. When there's only a small number, short chain, low energy, low boiling points. Bigger chain, longer, more forces, higher boiling point. Why is the boiling point higher? Well, you've got to put more energy in to get these molecules to break apart from each other. They're not as entangled with each other. It takes a lot of energy if they've attached in 5 or 6 different places. You've got to pull really hard. That means you've got to put in more energy. Remember, when you're wanting to get something to boil, you increase the energy, you raise the temperature, and that's what breaks things apart. Changes them from being liquids to being gases. Right, let's move on. Hope that's clear. Let's make sure that we've got the next question sorted. The next question says to us, how do the boiling points of the straight, very important, straight compounds differ from their corresponding isomers? Give a reason for the differences. for this difference. Okay, so let's have a look at our table again and compare these. I'm going to use an eraser just to take those off so we can get the data that we want. And we're looking back at the table and we're saying that one has a boiling point of -1, where this one, methyl propane, has a boiling point of -12. We recognize that the isomer is lower boiling point. Let's see if that trend, BPT, has a lower point. Let's see if the trend happens again. Pentane, the straight branch, 34, 28. Interesting. It's still lower. What about 68 compared to 58? Notice this is still lower. But notice the gap over here was the greatest. There's a big gap over there. Here there's a degree, 6 degrees difference. 6 degrees of difference, 6 degrees Celsius, whereas here it's about 10 degrees. Okay? So there's not much of a trend there, other than we can see that the boiling points of the isomers are definitely less than the straight chains. Why would that be? Can you think about it? Let's just understand what we mean by isomer. So I'm going to take two of them. I'm going to take butane and I'm going to take methyl propane. And I'm going to draw those structures for you so that you can compare them. So butane would look something like this. The structural isomer looks like this. There's an H, 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 and H. And we say this is butane, C4H10. Okay? Now, we wanted methyl propane. Methyl propane is only going to have 3 carbons in the longest chain. Notice that it is still C4H10. We'll see that in a minute. Still C4H10, but there's a methyl group over here in the middle. So what's happened to the length of the chain? Can you see it's got shorter? It's not as long. It's got more compact because you've got this side branch over here. So because it's shorter, the side branch means that there's not as many places to make an attachment. It means that we've got a smaller molecule. And if we had to compare a bigger molecule and its isomer, what we'd recognize, these molecules are no longer so slinky. They become more spherical. It's more spherical. And if it's more spherical, there's less space, and therefore less forces. Okay. Please notice they have the same molecular formula but different structures. That's why we call these isomers. The one that is a smaller one, the isomer that is not that is branched, has the lower boiling point. Less forces, lower boiling point. Got it? Hope so. Right, let's move on. And we come to question number 2. And we've done the first part. It says define structural isomers. We're simply going to say, well, we know what that is. It says it's the same molecular formula, but a different structure. Different structure. Structural formula. And we've illustrated it already. So I'm not even going to spend more time on that. I'm going to go straight on to the next part of the question. It says, write down the structural formula of these 2 isomers, and next to each, its IUPAC name. So let's go back to the top of the question, and it says there are 2 structural isomers for the organic compound with molecular formula C2H4O2. Okay, C2H4O2. C2H4. Sorry, I knew I'd made a mistake when I wrote it, but let's get it right. C2H4O2. That's the molecular structure. Now we need to get the structural isomers. And we need to write down its IUPAC name. So very quickly, I'm going to try and get this right. And the first one, I'm seeing oxygen like that, one oxygen there, and I'm going to make it a carboxylic acid. What is this called? This has got 2 carbons, so it is eth, and we're going to say it's single bond ethanoic acid. And it's one of my favorite, it's another word for vinegar, acetic acid, ethanoic acid, and it's very important because it's got hydrogen bonds that form. I did illustrate that earlier. What's an isomer of this? My other favorite one. It's an ester. Here we go. And we're going to call this 2 bonds, 2 bonds, 3 bonds over there, and there we've got it. This is going to be called methyl methanoate. Okay? This is an ester carboxylic acid. Right. State with each one, which one of these isomers has the higher boiling point. Now, guys, the one with the stronger forces. So it's the carboxylic acid, which is ethanoic acid. Ethanoic acids, higher boiling point. Which one has the higher vapor pressure? Very interesting. Now, guys, we need to understand vapor pressure before we answer this question. Vapor pressure is what pushes down on the liquid, and the one that has the higher vapor pressure, okay, so the liquid evaporates and pushes down. The one that has the higher vapor pressure will actually have the lower boiling point. So the one that is more fragrant, and that's going to be your ester, which is methyl methanoate.
I'm sure you've seen the walk together photo on our page. Please post a caption and like the captions that you think are best. The 3 captions with the most likes will each win a pair of tummy tackies. We'll post the winners on Friday, so get to liking and get all your friends to like too. Now it's time to take a break, so don't go away. We'll be right back. Welcome back from the break. I know you can't wait for the term to end and for the holidays to start. This year we bring you revision sessions from term 1 from the 28th of March till the 6th of April. These will be repeats of all the Learn Extra live shows from term 1. These programs will run from 9 a.m. in the morning till 7 p.m. at night. Go to our website learn.mindset.co.za for all the details. But for now, let's get back to the revision.
Let's revise and let's go over what this is. Some organic reactions are shown below, so let's just make sure we've got them. Let's use a nice bright color, and I might need to just go over this diagram. We've got X over there. We know that there's Br2 in UV light, and it gives us 1 bromopropane. Okay? That's the one thing. Then we've got propanol, and 1-ol, and it forms bromopropane, 1 bromopropane. We've got prop and 1-ol over here, and we've got concentrated potassium hydroxide and heat, and we make Y. Now, the alarm bells should be ringing. You should be remembering exactly what we've done, because we've mentioned all of these reactions in our little summary. So let's make sure that we can name the reactions illustrated by A, B, C, and D. So first of all, let's start off with A. So when A goes from X, and we don't know what X is, but we've given the clue that it's bromine that is being used, and we make 1 bromopropane. 1 bromopropane. It's not saying this is the whole reaction. Okay? Just saying it's one bromopropane. Now, be very careful here. When you've got bromine in UV light is essential. That will only happen when you have got substitution. So A is an example of substitution. Substitution. And what are we adding? We are adding, you don't need to do this, but we are adding a bromine atom. Please notice that it was just adding one bromine. If it was addition, then we'd have to add two bromines across a double bond. But at this stage, I reckon that we've got substitution there. Next one, number B. We start with propanol, propan-1-ol, and we end up with 1-bromopropane. So notice it's the number of carbons hasn't changed. This one was C3H7OH, and this one is C3H7Br. Can you see that what's happened is that? So what do you think has happened? That what we've gone is we were OH, and now we are Br. What do you think? I think it's substitution. So number B is also an example of substitution. What did we substitute? We took out, we removed the OH, and we changed it for a Br, just so that you can identify what's happened in that point. But now, we're not writing the chemistry there, so please don't get upset when I've said Br. Br can't be on its own. What about number C? It's gone back to being OH. So what have we done? We've taken the Br and we've replaced it with an OH. So again, number C, it's substitution. And in this case, it's the reverse of what we had there before. We started with the Br, we started with the bromine on that end, and we've replaced it with a hydroxyl group. Okay, we've replaced it with the hydroxyl group. And the last one, A, B, C, and D. So if we take concentrated potassium hydroxide and we heat this, yes, you're going to do substitution again. So all of them are examples of substitution reactions, and we're replacing those things. Use condensed structural formula to write a balanced equation for C. Now, reaction C was when we went from the 1-bromopropane to the propanol, propan-1-ol. So let's make sure that we've got it right. So we've got prop is 3, and we want condensed structural formula. We don't want to misread the instructions. So we must not just write the molecular formula. Remember, this formula is a molecular formula. We don't want that. We want to show the bonds, but we're going to show the hydrogen bonds there. We're going to show that there are 3 hydrogens over there. Remember that that's one end. Then we're going to do 2 hydrogens over there. We're going to do a hydrogen over here, plus there are 2 hydrogens over there, plus the bromine. So that will give you your condensed structural formula. I could have drawn them a little bit closer together, but I didn't, and perhaps I was wrong with doing that. Then with C, we want to get to OH, taking its place. So what we can do is we can simply say, let's take hydrogen and water, in other words, and we're going to say H2O. Now, because it said condensed structural formula, I don't think I need to give the whole thing. I can do it like that. And what I'm going to end up with is CH H3C, CH2, and CH2, and here's the important thing, OH plus HBr. So there we go, we've got a substitution taking place. It's an example of a hydrogenation using the water. Okay, write down the structural formula for compound X. Now, let's have a look where X is. It's up over there. Now, what I said to you originally, it's adding one bromine. So the structural formula must have been without the bromine. And it's likely, but they haven't told you, but because of what I think it is, I'm going to say that it would be in hydrogens, most likely to be the hydrogen just simply there. So if we take a look at it, in UV light, it's just the alkane, so it's likely that this is an alkane. So we're going to say C3H6. Write down the structural formula. Structural formula must show all the bonds, and that means C3, not H6, but H8. Okay. In order to obtain product Y, okay, let's have a look. That 1-bromopropane, product Y is this one. What it tells you, it was heated with potassium hydroxide. So it's heated with a concentrated solution under reflux, used condensed structural formula to write a balanced equation for the reaction. Now, again, we need to get balanced equation with the structural formula. This is a little bit tedious because it's all the structural formulas. Condensed structural formula, CH2Br. Now, when we add add in the potassium hydroxide, we're going to show it like that, and do the balanced equation again to balance it. We're simply saying that hydroxyl group is going to take the place of the bromine, and we're going to get KBr as one of the products. Last one for this question. It says a group of learners decided to heat that with sodium hydroxide instead of using concentrated under reflux. Write down the IUPAC name of the organic compound that they'll form. So now they're using dilute sodium hydroxide, and they're heating it as well. So we want the IUPAC name. Guys, you've got to remember the substitutions that are happening here. So let's just go back to our summary notes and make sure that we've got these correct, and so that you can be very clear that you've got them sorted out. So notice here the haloalkane plus water plus potassium hydroxide. We've got to dissolve it, we've got to heat it, and what we're going to form, we're going to form the alcohol plus the HX. So let's apply that knowledge. It's a different reaction using different products. But we're going to form the IUPAC with the alcohol. So over here we've got let's just draw the molecular formula, C3H7OH. Now if we want to get the IUPAC name of that, draw the structure out. We've drawn it a couple of times already, and you'll see that it's not too difficult to get that. It's prop and 1-ol. Okay, the position of the OH obviously depends on the bromine, and if it's in a different position, the bromine's in a different position, then it could become a secondary alcohol, meaning it's in the middle of the chain. Right, let's move on from there, and let's have a look at the next question. It says most organic can undergo substitution or addition or elimination reactions. They produce a big variety. There are some incomplete ones over here. So reaction 1, reaction 2, reaction 3, and we can have a look at that. Name the type of reaction represented by the third one. So here we've got reaction number 3. We're given something that's got a hydroxyl in it, and it's sulfuric acid and heat. Sulfuric acid is an amazing acid, but it's a very powerful oxidizing agent as well as a very powerful dehydrating agent. In this case, it will undergo dehydration. So what that means, it's going to remove that hydroxide and it's going to take it away, and a double bond is going to form. It's going to take that away, take away hydrogen from there as well, and we're going to get a double bond. So make sure that you understand that. It's an example of an elimination reaction. Good. Move on. Both reactions 1 and 2 are examples of addition reactions. I've told you that. Name the type of addition that is represented by each. So let's go back to it and have a look at it. What are we adding? In this case, we're adding water. If we're adding water, then it's hydration. And when we're adding HBr, that's hydrohalogenation. Okay, so when you add water, hydration, hydrohalogenation. These are both additions. We must give the specific name. So I've written that down. Then it says, write down the structural formula and the IUPAC name of the major product of reaction 1. So the major product of reaction 1, where we're getting the hydration, we're going to add in. Now notice that the double bond is in position number 1. We're going to break the double bond. We're going to add in how many carbons were there? Sorry, I didn't see that. It's CH3, CH2, CCH2. So that's 4. So I like to draw the structure, 4 carbons like that, and we are going to get the CH3. That's not going to change. The structural formula, put in all the hydrogens, that one, and now I'm going to put in a hydrogen over there. Now this is where you need to decide. Those are the hydrogens. We've broken the double bond. So where is the OH and where is the hydrogen going to go? We've got to add a water, an OH, and the hydroxyl likes to go on the end. Just like that. It's got more space on the end of the molecule. Doesn't like to be crowded out. And we've written the structure. Now we need to give the name. 1, 2, 3, 4. So 4 is bute, and it's an-1-ol. Okay.
We've come to the end of our show. Thank you so much, Mindsetters, for joining me and for chatting to me during the show. Remember to visit our website, learn.mindset.co.za, to get your notes and to watch the videos from the term. Goodbye.